Hi, we are the Husky Robotics team from the University of Washington. This is our critical design review video submission for the 2016 University Rover Challenge. Our team is structured into these subsystems. For each subsystem, we will overview our goals, how we have accomplished them, and what we still have left to do. At the end, we will discuss our resources and team schedule.
The chassis this year was focused on precise and agile steering with finite control, as well as a drive system that hugs the terrain. To accomplish this, we designed a split-body articulated steering inspired by large agricultural equipment. We use a differential drive system in each body to control the angle between the two bodies, and thus our turn radius and path. A twist motion was also integrated into the hinge segment to handle large slopes up to 60 degrees and irregularities in terrain such as rock gardens. We have a prototype made to test the steering system, and it performed well. For the suspension system, we decided on custom-built resilient wheels. These wheels are built using an aluminum outer rim with rubber lugs connected to a central hub with curved spring steel spokes. Currently, we are awaiting delivery of our main drive motors and only have 3 wheels left to manufacture and assemble for the entire chassis. We expect to be integrating with the other subsystems within 3 weeks.
This year, our arm and science systems will be separated in order to specialize for each task. For our arm and hand, our main goals were to increase our overall system rigidity, dexterity, and power. One change we have made was to allocate a larger portion of the overall rover weight to the arm. We have created a more compact turntable that also increases our structural stability. Instead of concentrating on degrees of freedom in our fragile wrist from last year, we have distributed them throughout the entire arm. Also, many of the joints which were previously powered by servos have now been changed into more powerful gear motors. Our hand has been redesigned from last year to have a larger motor and a better mechanical advantage in order to increase grip strength. We have 3D printed prototypes of our hand in order to confirm our calculations and design. Thus far, we have built the majority of our parts and are in our assembly phase of our design. After assembling the arm, we will be integrating with the chassis and begin testing.
For our science team, our main goals are to improve sample analysis on the rover and the reliability of our overall sample retrieval package. Our science system is utilizing an auger attached to a rack and pinion to obtain a sample from the required depth of 10 centimeters below the surface. We've intentionally designed our science system to have limited degrees of freedom, which, assuming defined ground geometries, will allow us to completely automate the sampling process. In addition to the subsurface temperature and humidity sensors, we will utilize the spectrometer as our third test to judge the composition of the soil to assess possible life conditions. We have assembled the main structure and are currently waiting for our size sensor to arrive. We are also currently working with the university's astrobiology department to better interpret our data.
This year, the goal of the electrical team is to produce a more robust system with easier serviceability and fewer individual modules. We're designing and manufacturing custom-printed circuit boards for each of the rover systems that will be able to function individually and will communicate with the main board to receive instructions. We are using the same microcontroller chip that is used on the Arduino Uno, taking full advantage of its open-source material. We have successfully tested all of the submodules individually and are currently working to integrate them together. We are finished with the designs and will be ordering the final boards and parts soon. The last steps are to assemble the incoming circuit boards and install them into our chassis.
The software team concentrated on improving reliability and user experience so we can consistently control the rover with an easy-to-use graphical user interface. With the GUI, we have an enhanced navigation system that allows us to see the rover's location and heading on a map. Camera feeds are also integrated into the GUI so the driver can see the rover's location and the camera feeds at the same time. For driving the rover, we use an exponential differential steering algorithm to control the turning rate of the two-body chassis. Our arm will also use inverse kinematics for easy and ergonomic control. We've already tested our wireless communication system and have switched to an omnidirectional antenna for the rover. Our system will operate on the 2.4 gigahertz range and be able to switch to any of the 11 channels operable within the United States. Also, to comply with FCC regulations, we have multiple members licensed with ham radio licenses.
We anticipate finishing construction in the upcoming weeks, allowing us the majority of next quarter to fix any issues that arise and allow time for team members to practice operating the rover. We currently have about $5,300 and expect to spend about $3,400 for the remaining parts. We are currently talking with department chairs to ask for support in case any unexpected major failures should occur. Trip costs will be mostly covered by our USEED crowdfunding campaign. Last year, we successfully raised $6,500, which greatly reduced trip costs paid by members. We would like to thank all of our sponsors for their support.